In lesson 2, we looked at x-intercepts and zeros of polynomials, and we discovered that whenever you have real zeros, that those are the x-intercepts of a polynomial. But if you have complex zeros, that means that you don't have any x-intercepts, or that those zeros do not show up as x-intercepts. So now what we're going to look at in lesson 3 is something called the discriminant. And the discriminant is something that we use for quadratic equations, and it helps us describe what the roots are going to be. So instead of actually trying to find the zeros and having to go through either the quadratic formula, completing the square, factoring, and actually figure out what those zeros are, the discriminant is kind of like a shortcut that you can use to determine the type of roots. So instead of actually finding out what the x values are, we can use a discriminant to help us describe the nature of the root. And again, the discriminant is only, so I'm going to add two things here, only used for quadratics, and it's used to describe the nature of the roots without solving. And when I say roots, remember these are the same thing as the zeros. So the formula for discriminant is this d equals, or the discriminant equals, b squared minus 4ac. And if you recall the quadratic formula, x equals negative b plus or minus square root b squared minus 4ac all over 2a. The discriminant is really the part underneath the square root. So that part underneath the square root is really what determines what kind of roots you're going to have, or what kind of zeros you're going to have. If you think about it, if this is a perfect square, that means you're going to have nice rational roots. So if I take the square root of a perfect square, it's going to come out to be a whole number, which means overall my answers would be rational. So that's this case here, that if we have a perfect square underneath, we're going to have two rational roots. Where if this number is not a perfect square, so let's say it's like square root of 2 is left, you're still going to have two real solutions. It's just that those numbers are going to be irrational. Because if you imagine taking the square root of 2, it's not going to come out nice, but you're still going to have a situation where your quadratic is going to cross the x-axis twice, creating two x-intercepts. So if it's a perfect square, you're going to have two rational numbers. If it's a non-perfect square as the discriminant, then you're going to have two irrational. And then the other two cases are if you get 0. So if you get 0, basically what that means is your graph is only going to have one x-intercept. It's going to hit the x-axis once. And if you think about it, the reason for that is if you had 0 under the square root, that would be like saying negative b plus or minus 0, which is basically like you don't need to worry about the plus or minus 0. So it would just be like saying negative b over 2a. And then lastly, the case here is the negative case. Well, if you get a negative number underneath the square root, that's when you're going to have an imaginary number. So you're going to have two complex solutions. And remember, we talked about this. Whenever you have complex solutions, your graph won't actually cross the x-axis because there won't be any x-intercepts. So let's look at some examples using the discriminant. So for these 4 examples, we want to determine the number of roots and the type of roots. So you could actually go through and solve these, but it's much shorter just to use this discriminant formula, so b squared minus 4ac. And you set it up the exact same way that you would set up the quadratic formula. We would identify a as 1, b is negative 3. Notice that I'm keeping those negative signs, and c is negative 40. And then what I do is I just plug in. So we have b, it's negative 3 squared, minus 4 times a, which is 1, times c, which is negative 40. And then you could just plug that whole thing in your calculator. You get a number, and you would get 169 for this. So basically, if you notice, 169 is a perfect square. So this is a positive perfect square. So that means if I were to solve this quadratic equation and I wanted to determine the number of solutions or the number of zeros, I would have to have two of them, and they would be two rational numbers. So two rational zeros or solutions. Remember that solutions, zeros, x-intercepts, roots, they're all pretty much the same thing. When we say x-intercepts, though, we do mean the real numbers because they have to cross the x-axis. So let's look at some other examples. So for this one, again, we're going to use the same formula. So let's just identify A, B, and C. And remember, whenever you identify A, B, and C, you have to make sure that your quadratic is in standard form. So now it's the discriminant equals B squared. Make sure that you're squaring this entire thing in parentheses so that you remember to square the negative. Minus 4a, which is 2, and then times c, which is 4. So we get 9 minus 32, so we get negative 23. So since we get a negative number here, I think negatives are the easiest to remember because remember, if you take the square, this is like the part under the square root in the quadratic formula. So if I take the square root of negative 23, I'm going to have a complex number. So this means you're going to have complex / imaginary roots. And you would have two of them because remember that complex roots occur in conjugate pairs. So you'd have to have, they would be conjugates of each other. So a plus bi and then a minus bi. And then this next one, so again, identify, make sure it's in standard form, which it is. And then we can plug in. So we have b squared, so negative 12 squared minus 4ac. So we get 144 minus 144, so we get 0. So since my discriminant is equal to 0, that means I'm only going to have one x-intercept. So I'm going to have one rational solution. So basically what this means is when you go to solve this, because remember it's an x squared, so that really means you're going to get two solutions out, but your two solutions are going to be the exact same. So this is what we call a repeated root, meaning it occurs twice. A repeated root or a repeated solution. So it would be like you would get out like, so let's say x equals 1, x equals 1. It's repeated, so it just means that your solution's repeated, but the x-intercept, there's only one of them. And then this last example here, notice it's not in standard form, so the first thing I need to do is I need to get this into standard form. So x squared plus 6x minus 8 equals 0. Identify a, b, and c is negative 8. And then we can plug in, so d equals b squared, so 6 squared minus 4a times c. So we have 36 minus 4 times 1 times negative 8. So we get 68. So this number here is positive, but it's not a perfect square. So it's positive, non-perfect square. So if you were to take the square root of 68, you would get an irrational number. So what that means for my x-intercepts or my solutions is that you're going to get two x-intercepts, but this time they're going to be irrational. So imagine taking the square root of 68, you would get irrational numbers, so your solutions are going to be irrational. So two irrational solutions. And again, when I say solutions, I could say roots, I could say zeros, or in this case, you can even say x-intercepts.